Hi guys, welcome to our channel of Sciences and Mathematics. I'm Ernest. Today we're going to look at basically a second description of these specific cyclic forms of carbohydrates. And we said that carbohydrates from the Fisher projection representation can be able to be given in form of cyclic forms, which basically we had already discussed in some of our videos. But for today, we're going to look at basically a summary of what we've already discussed in terms of basic points, which are going to assist us to describe a specific or a unique spatial arrangement for especially the forms of carbohydrates that we refer to as aldoses. Now I'm going to give two specific examples, basically in order to try and illustrate this specific unique case for the formation of cyclic forms of the carbohydrates. So without further ado, thank you and welcome. So as I've said, today we're going to look at a unique case for the spatial arrangement of these carbohydrates insofar as the transformation from the Fisher projection to the outward structure is concerned. And we said that this specific transformation that we said can be realized from this representation for the Fisher projection, whereby we have this molecule of sugar. Now I'm going to give just an hypothetical example. But basically, we're going to use specific examples in order to illustrate this specific arrangement for these structures. Now, suppose I have basically this like an hypothetical representation for the Fisher projection, and therefore we're going to take or have a consideration for these specific positions for those OH group, and basically these are going to determine the nature of a product that is going to be formed. And basically, we're going to concentrate on carbon number 3 and 4, or basically this specific range of carbons that are appearing at the higher level of these stereogenic centers. Now, I'm going to just have a summary of what we have already discussed to give us a clue on how we can be able to represent this special category of the overt structure and basically other configurations that we've already mentioned for D and L, negative and positive, respectively. Now, in this case, I'm going to rely on this specific concept that we've said. Now, for us to realize the cyclic forms of carbohydrates that we said that we have two specific groups. That's the functional group for aldehydes, which are basically mentioned together with the OH group, which are undergoing a rearrangement in order to form a cyclic set of forms of these specific sugars. Now, basically, I'm going to go through this summary in a short time so that we can be able to comprehend. Now, Emil Fischer came up with a specific representation for trying to show the formula, the projection for that was being applied to the enantiomers of this specific compound. That is glyceraldehyde. This one basically is a compound that is 2,3-dihydroxypropanol, and just give it 2,3-dihydroxy. It's a continuation propanol. So basically, this specific configuration that was assigned to this specific compound gives us a basis for this specific naming of this compound that we call the Fischer projection formula. Now, in this case, according to Fischer projection, the spatial arrangement for these specific groups determine whether the molecule can be given a configuration for either positive or negative. And for molecules that are like this one for 2,3-dihydroxypropanol, that is having this OH group that is facing to the right, was given a configuration for positive. And this one that was facing the left, this specific molecule, was given the configuration for negative. And therefore, if we try to look at this one and its specific enantiomer, if I give this one as compound A and B, compound B is an enantiomer of compound A, and therefore it's going to be given a name as a positive glyceraldehyde, and this is negative glyceraldehyde. For the two compounds respectively. So in this case, according to Fisher projection, we're going to give a particular configuration for negative and positive according to those specific positions for the OH group in this molecule. Now these two stereochemicals can further be defined according to the, be given a unique configuration for D and L. This one stands for dextro, and this is for liver, basically, which implies that this is an orientation for the right position for the OH group, and this is the orientation for the left position of those OH group. Now, if we have a consideration for these two specific molecules, and we can be able to assign those enantiomers an absolute configuration for L and D, whereby we're going to see that for enantiomer, which is the first one, therefore we're going to look at the position of the OH group. Therefore, for the first enantiomer that is having the OH group that is facing to the right is going to be given an absolute configuration for D, which is meaning that it's facing the right. So I'm just going to do away with this so that we can give this configuration to this molecule. We have said that for the OH group facing the right is given the positive aldehyde, and therefore we can be able to give this additional configuration for this for naming of dextro and levo respectively. So therefore, for a molecule of OH still that is facing the right, for the D and L configuration, we're going to give it a D, therefore positive glyceraldehyde. And then molecule that is, the substance that is having this specific orientation for the left side, and therefore we're going to give it as L levo negative glyceraldehyde. And therefore, from this specific two kind of illustration for the D and L and the positive and negative, we can be able to assign other molecules that are having a similar spatial arrangement for the two molecules using the configuration for D and L, or positive and negative, as I've illustrated on the board. Now we're going to look at a specific kind of molecules, especially of a higher class, now that we have seen using this specific example. Now, there's a point that I want us to highlight in this specific juncture, whereby as we can see that this specific molecule has got, for the enantiomers, this specific molecule for glyceraldehyde has got just a single stereogenic center. Now suppose we consider a case whereby we're having 2 or 3 stereogenic center, then we're going to have a specific way in which we're going to consider this specific naming system. Now my next illustration is going to give us a clue on how we are going to handle this specific case, insofar as molecules with 1 or perhaps 2 or more stereogenic centers can be able to be handled. Now for this specific kind of arrangement that I've mentioned for molecules with more than 1 chiral center, we're going to consider the case of erythrose, which is basically a sugar that I've illustrated on the board. So we can see that from this specific case we have 2 stereogenic centers, the first one being here and the second one being here. Let me just number them 1 and 2 so that we can be able to use those specific numbers in this specific case. Now we're going to look at this orientation for this and try to name it according to the Fisher projection. We can see that this substitution for point number, carbon number 1, the stereogenic center number 1 and 2 have got a OH group and they're facing the right. Therefore, we're going to give them the orientation for the erythrose. Now, suppose we have an enantiomer for this specific kind of a sugar, then we're going to have this one represented as such, and the orientation for the OH group is basically going to change and have that specific illustration. Therefore, for this, since it's facing the left, then therefore we're going to have to give a configuration for this specific sugar as L-erythrose. And if we consider a case whereby we are having a different spatial arrangement for this specific enantiomer, let's consider a case whereby this first molecule perhaps is having this kind of substituents. whereby we have a OH group at this specific point, and then we have another one which is at this specific point. Just going to give this. Now I've drawn this specific molecule together with its enantiomer, so we are having this mirror line at this specific point. We can see that this arrangement for this hydroxide group are alternating for this one and its specific mirror image. So in this case, we're going to have a naming of this specific compound according to the D and L configuration, considering a specific factor which I'm going to mention right now. So we have this stereogenic center for this first one as 1, 2, and this second one as 1, 2. So we're going to consider the position of the numbering of these stereogenic centers, and therefore the stereogenic center with the highest, we're going to consider the stereogenic center with the highest number. So this is the highest numbered stereogenic center is going to be considered for this specific allocation of our D and L for this substitution for OH group. Therefore, for the first one, if we find that the OH group is at our right side, therefore we're going to give it a configuration for D, and therefore we're going to name this particular sugar as D triose. These are different kind of a sugar, so therefore we're going to have a configuration for this given as D, considering that the highest numbered OH position is given as D. And if we consider the second one, then therefore we're going to see that it's 1, 2, therefore it's facing the left. So therefore it's going to assume an L configuration, which is anthraeose, given such. So this case of considering the highest numbered stereogenic centers is going to give us the naming of this specific molecules. Now there are different molecules that we're going to come across, but basically that's the same allocation that we're going to give for molecules of this specific kind. Now to achieve the cyclic forms of these carbohydrates, we see that there's going to be arrangement or perhaps a nucleophilic addition of the anomeric carbon together with the OH group at this specific point. So we're going to have an arrangement whereby this specific molecule is going to be formed, whereby we have that specific rearrangement for the OH group and the carbonyl carbon at this point. So the arrangement that is going to occur for this particular kind of a molecule, basically for formation of a furanose, is going to be realized due to this lone pair of electrons at this specific point, which are going to have a nucleophilic addition reaction for that one, and this double bond is going to move there. And the lone pairs of electrons from this point is going to pick on that particular proton, and therefore we're going to have a cyclic form of this compound, which is going to be illustrated as this. So in this specific molecule, we're going to have a 5-membered imiacetal form that is going to be referred to as a furanose substrate. So basically of interest for us is to try and figure out or try to see that specific carbon that we're going to refer to as anomeric carbon that has undergone a rearrangement. Basically, sometimes we can call this one as a carbonyl carbon, which is transforming to a cyclic form that we refer to as this specific carbon as anomeric carbon. Now the anomeric carbon, we're going to mention it in other various discussions that we are going to have. So basically, it's of essence for us to try and realize, perhaps understand the position of that one insofar as these rearrangements are concerned. So we can also have a 6-membered ring that is going to be formed from this specific collection. Now suppose we had a molecule which is having this particular representation for the condensed structure. This is going to form a 6-membered ring for this imiacet of this particular sugar. Now this is going to be pyranose. So therefore we can just have a similar arrangement for that. So I'm going to have this one just as a summary, whereby we're going to have this one being given as this. So as I've illustrated for the first one, then we are going to have for this rearrangement, those lone pairs of electron nucleophilic addition reaction is going to occur there. This is going to pick on that proton, and we're going to have a cyclic form of this specific compound that is going to appear like this. And that carbonyl carbon, therefore, we're going to have an OH group with this. So these other positions for the carbon group, I assume that we're just having a cyclic form of this structure. And therefore, since we do not have another OH group at this specific rearrangement, except the one that has undergone rearrangement with a carbon-carbon, therefore I'm going to assume that the H2 groups are those specific point. So from this basic concept, therefore, we're going to see that there's a unique way in which these particular cases for the aldehyde and OH group that are mentioned, which are undergoing a rearrangement, are no longer going to be considered as pairs in this case, whereby we're going to see that now the next reaction, or rather rearrangement, is going to occur between the aldehyde and the OH group at carbon number 4 for the higher sugars, and I'm going to give an illustration for that. Now suppose we have a pentose sugar of this specific illustration that we can name as ribose. We said that when we're discussing the concept of ribonucleic acid and dioxyribonucleic acid in one of our discussions, we said that ribose is a sugar of a pentose class. So as we can see, this is a 5-member carbon. Therefore, we're going to see this specific rearrangement forming these cyclic forms of carbohydrates. And as we said, we have already discussed the concept of DL and positive and negative. Therefore, I'm going to presume that the next structure that I'm going to put for this illustration is going to be comprehensive for us. Now, I've just given a second illustration, but there are specific points that I'd like us to note before we proceed to this specific mechanism. And we're going to see that the cyclic forms of sugars are also going to be classified as alpha or beta. Apart from the configuration that we have given them for the dextro, LIVO, and positive and negative. And therefore, in this consideration for alpha and beta, the products that we are going to attain from this specific rearrangement can be given a configuration for alpha and beta based on the configuration at the anomeric carbon that I've already mentioned. So generally, we're going to see that the D series, which is having the OH group to the right, a molecule is classified as alpha if the anomeric OH group faces down. So if we are going to see that there's an OH group that is going to be attached at this specific carbon, which is anomeric carbon. So we refer that one to as the anomeric OH group. If there's a substitution of the OH group that is at this specific point, then we're going to refer to it as anomeric OH group. So that's the one I'm mentioning. So therefore, according to this one, we're going to see that for the D series, as I've said, a molecule that is classified as alpha in the anomeric group when the OH group is facing down. So basically for alpha, denotation is going to have an OH group that is facing down. And conversely, therefore, we're going to see that for the beta group, the OH group is going to face up. Now, considering for the case of the L and D series, as I have already said, we're going to see that for the L series, a molecule that is going to be considered as alpha, as I said, if the anomeric carbon is facing, if the anomeric carbon OH group is facing down. Now, basically, this one applies, the two cases apply for the D series, which I've mentioned. Now, suppose we have a L series, which the OH group are facing the left, then we're going to see that for the L series, a molecule will be considered as alpha if the anomeric carbon is basically facing up. So if the anomeric carbon OH group is facing up, and beta, the anomeric carbon OH group is facing down. And therefore, we're going to see that this specific denotation is going to be given for the L series. So let's try to consider those specific cases. And I can repeat and say that for the alpha and beta series for the D group is going to be allocated for if a numeric OH group is facing down. For the D series, it's going to be given as alpha. If the numeric OH group for the D series is facing up, then we're going to give it as beta. For L group or series, we're going to have the OH group at the numeric carbon facing up for the alpha denotation. And then for the L series, we're going to have a numeric OH group facing down, and it's going to be beta. So I hope that those two differences are noted. Therefore, if you can be able to try and proceed from this specific point, then therefore the two conditions that I've mentioned at this specific point are going to give us the basis for the naming of our structures that we refer to as the Howard structures, which are basically given a denotation for B, beta, and alpha, apart from the D and L series respectively. So in this case, the products that we're going to attain from that, as I mentioned, are going to display this specific property. And therefore, let's proceed for our mechanism in this case. So as we can see, the one that are facing the Fischer projection facing the right OH group are facing down in this specific rearrangement, which is basically going to form a basis for us, as I said, for the Howard structure representation for this molecule. So if we try to look at this particular case for the first and the second illustration that I've mentioned from this Fischer projection, we can be able to name this molecule starting from this point as carbon number 1, 2, 3, 4, and 5 respectively. If I try to give the same representation for this specific case from the aldehyde group, then we're going to have this one as carbon number 1, 2, 3, 4, 5. Now if we compare this specific rearrangement, then I can still be able to give this one as 1, 2, 3, 4, 5. So therefore, if you try to look at the specific arrangement for carbon number 4 and 5, so carbon number 4 and 5, carbon 5, sorry for that, we're going to see that there's a specific orientation that has been able to be achieved from the first to the second case, whereby we're going to see that there's a rotation at carbon number 4 and 5 in order for us to achieve that specific arrangement. So in this case, this is going to be the rotation about the carbon number 4 and 5. And therefore, unlike that case whereby we were having a rearrangement that is taking place between the alcohol group and the aldehyde group at these two specific points, this OH group at carbon number 4 is the one that has been rearranged to appear at that specific point. So unlike the normal cases whereby we were having a rearrangement at this specific point, the OH group is going to take part in this specific formation of the neacetal, a form of this group. So therefore, we're going to have these lone pairs of electron at those specific points taking part in that nucleophilic addition. So we're going to have this one attack at that specific point, and this is going to be on that proton. And therefore, that is going to result in two forms of specifically two stereochemicals from that specific product, which I'm going to illustrate shortly. So if we try to compare these specific two products, we're going to see that this specific rearrangement is basically the same as this, only that there's a difference in the spatial arrangement of this specific OH, that numeric carbon. So this is the first and the second product respectively. Therefore, in assigning the alpha and beta configuration for this molecule of basically, this is a glucose. Just a minute. No, this is not a glucose. So therefore, we're going to just have a rearrangement of this specific molecule and try to see how we can be able to represent it. This is basically a ribose sugar, and therefore we are going to have this rearrangement being given. So if we consider so basically there's a clarity that I want to make, because I see that this representation for the end product, especially concerning the rotation, is not correct. So this basic arrangement to realize this OH at this specific point was going to be represented at this specific carbon number 3 and 4, contrary to the 4 and 5 that we have mentioned. So basically we can do that correction. So therefore that is okay. So from there we're going to see that the specific position for the OH group at this specific point is going to give us those two products for this ribose sugar. So therefore, as we said, for us to achieve those ribofuranosis products that I've mentioned, we're going to see that the first one, as we said, the OH group is going to face down in this specific D series. And since these byproducts as a result of the D series from the Fischer projection, therefore the first one, for this one that is facing down, we're going to have the alpha D ribose sugar, so it's going to be a ribofranose. And therefore for the second one, it's going to be facing up beta D ribofranose. So we're going to achieve the two products. Now, essence for us is to take note of this specific rotation, so that we can be able to contrast it from the previous examples that we have been doing regarding this specific formation of the cyclic compounds, where it involves the reaction between an OH group and basically the aldehyde groups. Now, in this case, it is resulting from the rearrangement of this specific carbon due to the rotation at carbon number 3 and 4. So I hope that the summary that we have given for those specific reactions and the last bit that we have discussed, of course, on these cyclic forms of carbohydrates by giving this ribose sugar as an example, it's going to shed light for us on how we can be able to conform, of course, or rather try to give a confirmation of this specific representation for sugars, and also try to match the ideas of the DL configuration, the positive, negative, basically which are the Howard structure, Fischer projection, two of them ideas, so that we can come up with these products. So I'd like to encourage our members to go and check out on our description box. There's a link for the other discussions that we have had on the same topic, so that together they can just assist us to comprehend this topic in its entirety. So that is it for today, guys. Bye, my God bless you.